Happy belated December ween, babes! And what better way to celebrate than talking about eye function? That's right, various boys and also additionally girls, we are talking about those delicious and occasionally equally nutritious face balls you keep in your skull and the groovy components therein. When dealing with the parts inside your face balls, it's best to assume that they are arranged the reverse of what you might assume, at least in vertebrates. Let's start with those sweet, sweet rods and cones. Look at them! Look at them beauties! I'd love for an architect to design buildings based off them. Anyways, let's start with those rods. Rods don't need a lot of light to activate and are great for vision in low light environments. However, they aren't designed for color differentiation and translate their information in grayscale. Even if we aren't consciously aware of it, we see in black and white when light levels are very, very low. Animals with better night vision than us have eyes packed with more rods than they do cones. Cones themselves are their pointy bits that translate differing wavelengths of light into colors, though each cone is specifically designed to translate an individual color. In other words, it's one pigment per cone. Though the spectrum of wavelengths is quite broad, different animals have different cone setups. Like some arthropods see an ultraviolet end of the spectrum, while our goofy butts are set up for the classic RGB system. Both rods and cones are set up along the inner lining of a retina, with cones being more concentrated towards the fovea and rods filling everywhere else. One of my favorite professors told the story of soldiers heavily utilizing their peripheral vision in dark conditions. As you can see in this diagram, the fovea is designed right behind the pupil for direct reception, while it's the optic nerve structure that's a wee bit offset. And here's where we get into the backwards built stuff. Rod pathways release glutamate neurotransmitters when dark, but, and it's a big but, they stop firing when light is present, the opposite of what you might expect. If you look at the way rods and cones are arranged along the retina, you'll see they face the wall, while the wiring is exposed to incoming photons. This means the photons have to zipple-zapple their way past all kinds of structures before they reach the rods or cones. Vertebrate eyes are built like this. However, invertebrates have their rods and cones facing the ways you might expect them to. Towards incoming photons. Before we talk about photons hitting the structures, we need to get to know two new friends, chromophore and opsin. Opsin is a group of light-sensitive proteins that convert specific wavelengths of light into specific electrochemical signals for our neurons and brainy bits to translate. Chromophores are, according to my professorman, biological molecules that serve to capture or detect light energy. The chromophore is the moiety that causes a conformational change of the molecule when hit by light. What do all them there photons have to pass through to make it to the rods and cones? Oh, here are all the cell layers. Ganglion, amacrine, bipolar, horizontal. Then the rods and cones themselves as they face away from incoming light. If you memorize better via acronyms, recall that it's the sound you might make while stubbing your toe or looking at your tax returns. Or stubbing your toe on your tax returns. Either way, it's easier than recalling Fahuglagods. I hope you're a big fan of more backwards built bio, because not only are vertebrate rods and cones facing an odd direction, but their signaling method is even more funky. We'll cover that a bit in part 2 of our Faceball journey. Do a man jig, do a like button, hoot on the subscriptions, share it with your grandma, share it with her knitting circle.